Knowledge is of no value unless you put it into practice, said Anton Chekhov. Indeed, the value of knowledge lies in its application. Finding derivatives, the goal of differentiation, is powered by knowledge. We need a deep understanding of the domain we are studying to effectively find derivatives. Furthermore, to me, it gets better than this too. Derivatives are often discovered as quantities that emerge from understanding changes in something. Over the next 3 lessons, we will discover the meaning of derivatives through a deep dive into the respective domain knowledge. Obviously, the domain background in the lessons is limited to the lesson goals, which aim to present a nuanced appreciation of why we seek derivatives. There are 4 case studies, each illustrating different reasons for taking recourse to derivatives. The first is about the critical importance of derivatives, using examples of rainfall rate and electric current, both of which are derivatives. The second is a classical case explanation of what derivatives are. The third case study is about how 2 derivatives of the same thing could offer different meanings, accurately describing change in things. Things that change quantitatively in some way, such as the speed of a moving object or the size of an inflating balloon, can only be accurately understood or described by a series of its values at many instants of time, or any other changing quantity such as volume of air. We will explore a few but diverse domains where the rate of change or the derivatives plays a critical role. Climatology. The importance of knowing instantaneous rainfall rates, the frequency of high rainfall occurrences, and the instantaneous rainfall rate, which is the amount of rainfall in a very short period, are valuable for designing communication systems such that the selected microwave frequencies and power levels of ground and satellite radars can handle various weather conditions. Designing supersonic vehicles, jets, as the erosion and wear and tear due to rainfall rates affect the material and structural design. Instantaneous rainfall rates. Relatively long-period rainfall rates are not useful in designing supersonic vehicles and selecting microwave frequencies and power levels. They miss the real impact of rainfall in short bursts that matter for these applications. Instantaneous rainfall rates is needed for the best performance of such vehicles or communication systems. Interestingly, 1-minute interval is the shortest time interval for which an instantaneous rainfall rate could be obtained. Is a 1-minute rate instantaneous enough? Yes. Experimentally, it has been found that the frequencies of the instantaneous rainfall accurately measured for periods less than 1 minute do not affect the working of the supersonic vehicles, radars, and communication systems that were designed based on the frequencies measured for a 1-minute interval. However, a burst of rainfall that lasts beyond a minute needs to be duly accounted for. Electrical circuits, their behavior linked to instantaneous surges. Electrical circuits are heavily influenced by 2 fundamental quantities, voltage and current. These variables play a crucial role in shaping the behavior and performance of electrical circuits and systems. By effectively controlling and monitoring voltage and current within a circuit, we can ensure that it operates as intended, thereby safeguarding the proper functioning and safety of its components. Common hazards affecting circuits. Overvoltage, when the voltage exceeds normal levels, resulting in increased current flow as more charge is pushed through the circuit. Recall the potential difference is expressed in volts. It is the force that pushes the charge to move between 2 points. Overvoltage is typically a power supply issue. Undervoltage. When the voltage is lower than normal, it also leads to increased current flow, but due to a different reason, the decrease in voltage from the power source. The power source in a circuit provides a fixed voltage, but variable current depending upon the circuit conditions. When voltage drops, the power source increases the current supply to maintain the energy or power required by the devices. Recall that electric power is the product of potential difference and current, overcurrent. This causes overheating of circuits, components, and devices. it can sometimes lead to undervoltage conditions. It is primarily due to excessive load or near no-load conditions. Pertinently, all three hazards are eventually conditions of overcurrent. Unlike voltage, current varies and is not fixed by the power source. Current and its instantaneous values play a critical role. Now we know that current and its instantaneous values need constant monitoring, as they play a critical role in protecting electrical circuits from various hazards. Voltage variations anyway stem from the power supply. It may be occasionally due to undercurrent too, making them easier to monitor. So, we will learn how to compute current and its instantaneous values. How can we measure current? We know that electric current is the flow of electric charge through an electrical conductor or space over time. We cannot measure current directly in the sense that it is not a direct count or measure of a physical thing in circuits. In fact, it involves measuring two quantities, the amount of charge flowing and the time over which it flows. This requires precise measurement of both charge and time. Ammeters are instruments used to measure the quantity of electric charge flowing per unit time, and we get the current value as the rate of such flow. Current, its instantaneous values. The value of the current at a particular point in a circuit and moment of time is computed from the value of the instantaneous flow of charge. Instantaneous current is the rate of change of electric charge over time. Recall that the rate of change is the quantity of change itself, if the unit of time is 1. Thus, if the unit of time is 1 second, then the amount of charge is the amount of current. Mathematically, current is the derivative of electric charge with respect to time. Because current is a derived quantity, it does not have a unit of measurement of its own. Ampere is derived out of the units of charge, that is, coulomb, and time in per second, the quantity of charge in coulombs, is directly measurable. A note on complex circuits. In more intricate electric circuits containing nonlinear components like semiconductors or time-varying signals such as AC signals calculating the instantaneous voltage, and current requires advanced mathematical tools such as differential equations. It could be extrapolated that these complex circuits exhibit dynamic relationships between voltage and current, which change over time. Differential equations are instrumental in understanding and relating these changing quantities. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.